So it's a great pleasure to have Chen Chen here from UCLA, and he's gonna talk about variance-dependent linear advanced for linear bandits and linear mixture MDPs, adaptivity and computational efficiency.
Thank you for the introduction, and yeah, I'm very excited to be here. So in this talk, I'm going to introduce our recent work, which is trying to derive some new algorithms which enjoy variance-dependent regression. So in most of this talk, I will focus on linear bandit problems, and in the end of this talk, I will briefly discuss the extension to very famous reinforcement learning model with linear approximation, which is called linear Adaptivity. So this is a joint work with my PhD student, He Yang Zhao, Jiaban He, Dongguo Zhou, and also my collaborator, Ling Zhang. So the background of this work is trying to study reinforcement learning with function approximation, in particular linear function approximation. And in many decision-making problems, actually the agent is doing decision-making in a heterogeneous environment. So in other words, if it's a bandit problems, at each round, the reward may follow a different distribution. And if it's, for example, market decision process, then we are considering, for example, time inhomogeneous market decision process or something like that. Or at least there's a state transition. And here's an example that motivates us to study this decision-making problems in a heteroscedastic environment. So suppose there's a recommendation system, for example, a recommendation system for restaurant. And every time when there's a user, for example, coming to the restaurant to choose which food to order, the restaurant will recommend a list of different meals to the users, and then user will pick one which they like. And if we just keep serving a single user, then this problem actually is a simple problem because there's only one user. But in reality, there are many users. There are many customers who will come into this restaurant. And some of the very easy or very reliable, for example, we recommend a list of food to this customer, and this customer always, for example, choose certain kind of food, for example, pizza or ice cream or something like that. While the other customers, their behavior may be more stochastic, for example, or sometimes even when the customer eats some food, even he or she doesn't like it, but they may still give you a very good rating. So this is a problem of estimating the, for example, the click-through rate based on different users' feedback. And we formulated this problem as a heteroscedastic stochastic linear bandit problem. So at each time run K, the environment will generate a decision set, which is denoted by EK. And then the agent or the user will observe this EK and then choose the arm from this decision set, which is denoted by AK. And then the agent will receive the reward, which is a linear function parameterized by sigma star plus some additive noise, eta k. Here, eta k can be different at different random Ks. That's why we call it heteroscedastic random noise. And more formally speaking, we assume the additive noise is bounded, and this assumption can be relaxed to be, for example, sub-Gaussian. And we assume the noise has conditional mean equal to 0, and the conditional variance is bounded by sigma k square. So here, the sigma k square actually is not a universal upper bound, actually it's upper bound for different time k, which means the noise is heteroscedastic, is heterogeneous across the time run. And the goal of this linear bandit problem is trying to find some algorithm or find some policy such that the cumulative reward will be maximized. Or in other words, we want to minimize the pseudo regret, which is defined as the theta bar, which is the underlying parameter with a vector for the linear function times AK star. So AK star is the optimal arm at time k, minus the inner product between theta star and AK, where AK is the arm picked by the algorithm. And this problem has been studied for quite a long time, especially in the homogeneous noise setting. It can at least date back to, for example, the work by Daniel, or we have an algorithm called Computational 2. And I think one of the mostly recognized and also cited work is by Abase, Yakudo, and co-authors. I think many authors are here. The algorithm is called OFUO, which is optimism in the face of uncertainty limit. And they can achieve a regret, the worst case regret, which is in the order of B times square root of K. So here K is the time horizon. And if the, for example, reward is deterministic, which means there's no active noise, their algorithm can also give B square root of K regret, but obviously this is not the best we can do, because if there's no random noise, and suppose the arm is of D dimension, then as long as you observe like D different contexts, then in principle you should be able to learn or estimate theta star very accurately. And then after that, you shouldn't suffer from any future regret. Okay, and this algorithm is very easy to implement, and it has been widely used in different applications. And 2 years ago, my student Dumor and collaborator Chaba, we come up with another algorithm which is called the weighted OFUL. The idea of weighted OFUL is we assume that at different time k, the noise, the variance information of the noise is available. And think about that when you do concentration inequality, if you don't have the variance information, then you use, for example, Houdin inequality. But if you have the variance information of a random variable, then you can use Boolean inequality, which can lead to some tighter upper bound. So this is the idea we come up with this algorithm. But actually, originally we want to solve an even more challenging problem, which is nearly max optimal regret for learning linear MDPs, which I'm not going to talk about it in this talk. But as of like the first step to tackle that problem, we studied this linear heteroscedastic linear bandits. And as you can see, by using weighted OFUO, we can achieve a regret bound, which is in order of D times square root of summation of sigma k squared all the way up to 10k, and then plus additional term, which is the square root of E times k. And in this case, you can see that suppose the reward is deterministic, then in that case, sigma k all equal to 0. Then the worst case regret in the deterministic case will reduce to square root of k. But it has a dependency on k, which is not optimal. And last year, we further improved this algorithm by using more careful importance weight design. And we reduced the regret from this 2 terms to the first term plus constant d without any polynomial dependence of k for this one. And then in the deterministic case, when there's no stochastic noise, the regret will reduce to this almost like a linear in D. However, this algorithm suffers a major drawback because we need to know the variance of the reward at each time, or at least the upper bound of the variance of the reward. Okay. And I have to mention that there are some other concurrent independent work, which is called OFUL by Zhang et al. And later it was improved by Kim et al. So their algorithm does not need to know the upper bound of the variance, but their algorithm is not computationally efficient because they need to construct some estimator which depend on exponential number of confidence set. So their algorithm is not easy to implement, and apparently is not computationally efficient. And also their dependence, no matter in the worst case or in the deterministic case, has a high degree polynomial dependence on the context vector dimension B. Okay. So this raises an open question: can we achieve computational efficiency and parameter free. Okay, so here parameter free means we don't need to know the first information of the reward. And in order to solve this open question, let me walk you through the very famous OFUR algorithm, and then the weighted OFUR algorithm. And eventually, I will introduce the algorithm we proposed that can achieve both computational efficiency and the parameter free. Okay. So the OFUR algorithm is based on the optimistic estimation of the reward, or simply speaking, based on the upper common bound of the reward. So they first conduct a ridge regression estimator based on the historical data up to time t, and then we get theta hat t. Given theta hat t, the algorithm will conduct a confidence set, which will include theta star, which is the true weight vector for underlying linear reward with factor b. And in the paper by Abasi, Yakori, and al., they prove a very nice concentration inequality, which is a Hoping type concentration inequality for self-normalized vector value modular. And based on that concentration inequality, they can conduct such kind of confidence bound with confidence radius proportional to equal to beta hat t. And here, beta hat t is in the order of r times square d. So remember that d is the input dimension, and r is the magnitude of the noise. And by using this confidence set, and also following some very nice and simple proof, we can show that the reward of OFUL is in the order of RD times square root t. And because they do not consider the variance information of the reward or the noise, so this is the best they can do, and actually it also match the lower bound when the decision set is of infinite size. And in our later work, we consider the variance of the noise or the variance of the reward. And then this motivates us to derive counterpart of the self-normalized marginal inequality in their paper, because we want to have some Gaussian type inequality which can leverage the variance information of the noise. So in our paper with my student and also with Chava, we derived the following, which actually I didn't put the full concentration inequality statement here, but we conduct the confidence set, which is equal to less than or equal to beta hat t, where beta hat t is in the order of sigma times square d plus r. So you can see that we somehow replace the r dependence in the term which depend on the dimension d by the standard deviation of the noise and then plus r. Okay, so we somehow separate this r from the dimension d. And in many cases, as long as the variance is less than the magnitude of the noise, then this confidence radius is much smaller. So this is the idea. However, if you look at this theorem, there's a condition. So the condition is that the variance of the noise is universally bounded by sigma square. So in other words, this sigma square doesn't depend on time t. So it's a universal upper bound. So suppose there are some time step, the variance is small, and some other time step, the variance is large. Then we have to use a large variance upper bound to define this sigma square. Okay, so which means this concentration inequality is not that adaptive to the variance of the noise. And because of this universal upper bound on the variance at different t, so we need to use the weighting technique to normalize the reward or the input output such that the variance of the normalized input output will be upper bounded by the same upper bound. So that's why we propose the following weighted regression estimator. So suppose we know the upper bound of reference at a different time t, then we just use the one of the variance upper bound as a weight to weight the square loss, and then we do this weighted regression. And when we do the regret proof, of course, we will just add this variance upper bound back to the calculation. And by doing that, we prove that this weighted OFUL algorithm, it can so it can achieve, like I said, this one, this regret, which is the D times the summation of the north variance plus throughout the decay. Okay. And as you can see, because in the weighted ridge regression estimator, we need to know the upper bound of the variance at each time, right? So this is something we need to know.
Oh, just going to ask, what is sigma bar?
Sigma bar. Here, sigma I square is the exact variance of the reward.
Yes, what's sigma bar?
And the sigma bar is the upper bound. As long as it's upper bound, then this algorithm works.
Oh, so you're going to estimate it an upper bound with high probability, or do you assume it's given?
We assume it's given.
Oh, but then does it scale with the actual variance, or does it scale with the upper bound?
You are right. But as long as
Sorry,
you
which
have
one?
in the proof, you can so if you just do this, actually in the required bound will be sigma I bar square.
Right.
But
so
if you know exact the variance, then this sigma bar I square will be replaced by sigma I square.
if you do what, sorry?
If you know the exact variance of the reward.
Right, but I thought we assumed we don't know the variance.
Oh no, the algorithm need to know the variance, or at least the upper bound of the variance.
But so just to confirm, the algorithm won't scale with the true variance, it will scale with a given parameter, which is an upper bound of the variance.
Yes.
Okay.
Yeah. Yes. Yeah, because this sigma I bar can be seen as a hyperparameter to the input of
Right, but it's okay. Yeah.
Yeah.
Thank you.
Yeah. All right. And so as I mentioned, because of the limitation of this Variance type inequality, where the variance upper bound actually does not depend on the different time t. So that's why we have to do this weighting technique. And because of doing the weighting, after we add this variance back into the regret proof, we will have, because we do this weighting, we need to know the variance information of the noise at each time step. And this motivates us to think about if we can prove some Friedman type inequality for self-normalized market. So by Friedman type inequality, I mean, if you look at the condition of this theory, so it's a conditional v equals 0, magnitude of noise bounded by R, which is same as before. But instead of assume the variance of the noise at each time step is bounded by the universal constant, we only need to assume the summation of the variance noise of the variance of the noise up to time k is bounded by some vk. And because of this, you can see that this upper bound actually depends on time k, which is more adaptive. But when we derive this kind of concentration inequality, we also need to add an additional condition, which is this performance need to be unbounded by some universal constant rho.
Sorry, is ZK the design matrix or is it a single direction?
This is AK? Oh, ZK is covariance matrix. This is AK.
Okay, yeah.
Summation. Yeah.
But it was normalized with the upper bounds of the variance or not, or
No,
is that okay?
yeah, it's just the original.
Okay.
Yeah, it's not normalized.
So if you were to do this one more step, if you were to now try to estimate an upper bound on sigma squared, and you would make some further assumption to an upper bound on hyperparameter, could you keep on going?
For the original algorithm, we can make the still keep going. But here we will estimate the variance of the noise at each time step.
Oh, so you're actually going to do this?
Yeah, we are going
Oh,
to actually.
sorry, I didn't realize that the previous thing wasn't your result. Okay, sorry.
No, this is the only result. So this is the only result. Yeah,
Sorry.
That's okay. Yeah. So as you can see, now we can conduct a function sine where the radius k is in this order. Okay, it's rho times square root of vk times some polynomial term depending on k, and then plus rho times r. And you can see that there's a trivial upper bound for rho. which is 1 over square root lambda. But if you plug in this trivial upper bound into the definition of beta k, this term is okay because still not over R, the same as before. But this one, you can see that it is a square root of Vk. But Vk is a summation of the variance of the noise, which can potentially depend on k linearly. Right. So as you remember previously, we have this sigma times square e. So the first term does not depend on k. And then if you use this constant set, constant radius, you follow the standard proof for linear bandit, you will get the square root k right. But here, this Vk may potentially depend on k, because it's summation of the variance of k random variables. Right. So this Vk may have some polynomial depending on k, which is our max. And how to solve this problem? So the solution to solve this problem is actually we can have a fine-grained control of this rho, because the worst case outbound of worst case magnitude of rho is like 1 over square root lambda. But if we partition the context into different layers according to this orders or uncertainty term, just like a superlinear algorithm, and we can divide this into, for example, 2 to the minus L multiple layers, and this will solve the problem. Yeah, question? What is Zk is the covariance matrix, empirical covariance matrix plus lambda times identity. Yeah. Okay. So is everything all clear? All right. So now let me introduce the superlinear UCD type algorithm, which is the algorithm proposed by Schreiber. But this kind of this multi-layer structure design actually was also I think used in some early papers. But this is superlinear algorithm. Superlinear UCD algorithm is proposed in Schreiber. So the algorithm actually will define at each time k, given, for example, arm AK, the algorithm will assign this AK into different layers or into different levels. Okay, so I will explain each of these conditions one by one so that it can help you better understand this idea. Okay, so here alpha is a very small term, for example, 1 over k or something like that. So it will start with check if the uncertainty of the arm A, all arm in the action set, is less than or equal to alpha. So this alpha is small enough number, which is in order of 1 over k. And if all the arms in the decision set is less than half, then it will just choose AK using the standard optimistic estimation. And then the context set with psi k will remain the same. So no need to update the observation history for estimation. And the second case is if for all the arms in the decision set, the bonus is less than or equal to 2 minus L. In this case, because the bonus of each, or the uncertainty of each arm is all small enough, so we can do arm elimination. And we will keep eliminating the arms which are not optimal arms if we cannot find an arm with a desired uncertainty. And in the last case, if we can find some arm AK whose uncertainty is larger than 2 minus L, and then we will define a weight, which is 2 minus L divided by the uncertainty of this arm, the bonus of this arm. And then we will add this arm with corresponding reward into the corresponding layer, which is a layer L. And for the other layers, it just remains the same. Okay. So in other words, the elimination process will start by selecting an action with large enough uncertainty. And why we choose this kind of way? So the reason will be immediately clear in the next few slides. Okay, now let me introduce the layer-wise estimator, because we divide the context into different layers, and at each layer there is a weighted ridge regression estimator to estimate sigma star, which is denoted by sigma height k, comma l. Okay, so k is the index of the round, and l is the index of the layer. And at layer L, we can prove that. And this is a very actually well-known solve. So if you are doing this layer-wise structure, we can show that the number of context vectors being added to layer L can be upper bounded by 2 to the 2L times D. And remember that L actually is in the order of log T. So this is actually not a big number. And then within this layer, we will do this weighted ridge regression with weight WI. And the WI actually is defined there, which is 2 to 9L divided by the bonus. And it is very easy to show that the bonus of the weighted context will equal to 2 to SL. And remember that in our newly derived Friedman type convention inequality, we need an upper bound for this bonus, which is denoted by rho. And now, using this multi-layer structure, we are able to ensure that at layer L, the bonus of the weighted context is upper bounded by 2 to minus L. Okay, so this is the key idea why we defined the weight as this is 2 to minus L divided by 1. Because if the weight is defined in that way, then the bonus of the weighted context will equal to 2 to the minus L. So in other words, we are doing peeling, algorithmic peeling on rho, instead of using worst case crude upper bound to upper bound that rho. Okay. So any question?
So my understanding of this superlinear layering trick was that it kind of moves us from the adaptive design to kind of a fixed design setting.
Exactly.
So the theorem uses this property.
Oh, this theorem does not use this property.
Yeah.
Yeah.
So then I'm wondering whether there is room for improvement there, because you think that all does have.
You're right. Actually, for linear banded setting, the reason we use this superlinear structure is because this structure is very well known in the banded literature. But later, when we extended to RL, actually, we somehow get rid of the superlinear structure. So in other words, even for linear banded, we don't need to use this superlinear kind of structure. As long as we can do this multi-layer structure, we can still get the same degree even for linear banded. But here I just use this superlinear structure as one of the possible way to implement this multi-layer structure, because many people know superlinear, so I go with superlinear.
I see. Because like based on the previous slide, I expected that you're just going to do peeling based on this quantity. And effectively the algorithm is doing the peeling, but I wish it was not the algorithm that was doing the peeling, but the bomb. So you have that result, the peeling result?
Yeah, we have the actually simple algorithm for bandit. So we don't. So in other words, we only need to do peeling just based on bonus. We don't need to use, for example, superlinear kind of
the compartmentalization of the data would not be needed, and you could just do the peeling and you're computing the confidence bound.
Okay.
Okay, just to clarify what Chava said, do you have like a confidence interval that looks like what you appear but doesn't require you to do anything special in the algorithm? Can you move forward into the analysis and not have to do anything special with the way to select those.
Okay.
Because I
Yeah.
don't care about super lean.
Yeah.
Going to type.
I think that this multi-layer structure is essential. It doesn't have to be super lean, but you have to.
Does algorithm have to do anything special? Okay,
You have to sort the data.
Yeah, we still need to partition the data according to their honors.
okay.
So this algorithm peeling, I think, is unaffordable.
What's that going to cost you? Like what's because super OLED, yes, breakdowns doesn't work.
In the sense that if you implement it
If you
on
try
a
running it.
simplest problem, you have to wait until the end of the universe before the regret curve starts to bend a little bit,
Yeah.
right?
So I'm personally not fun. I'm wondering how much of the super OLED of this layering is going to bleed into the algorithm.
Oh, I think the multi-layer is a partition is essential. I don't know how to get rid of it. But the super lean is not essential.
Okay.
Super lean, because super lean, those three conditions, I think it's not necessary.
Okay. So the peeling is essential, but you're not using the sort of independence given by super OLED.
Yeah, we don't need that. It's independence.
You don't give up independence.
Yeah.
And I know this is a rogue question, but have you actually tried this in practice?
Oh, we didn't implement this algorithm.
Okay.
And the reason why we do not use super lean is because if we do super lean, actually, because it's doing ARM elimination, so we can only deal with, because the super lean needs to do ARM elimination.
Yes.
Then it can only deal with the finite part of that.
Sure.
But in our second algorithm, which is
So something better is coming.
yeah, you can deal with infinite size.
I'll wait until the end.
Okay, but that one will be very brief, but it will be very detailed in the paper. Yeah. All right. Now, there's one more remaining question we need to resolve, because now we have this explicit control of this row by using this multi-layer structure. But we still need to know VK, which is the summation of the summation of the products of the nodes. So we still need to estimate this VK, right? And how to do that? We can use just the sum of the one point plotting estimation. So remember that the definition of sigma I is that, and we just replace this sigma star by estimator's hypercale using this one plot plotting estimation, and then we add it together. And there's a combination called with pool. So this is weighted variance, and the other boundary diagram is empirical weighted variance. Weighted empirical variance plus some R square or K terms, and also lower boundary line is weighted empirical variance minus this R square very low.
So in a sense, the trick is that since you move to the sum of the variances,
Yeah.
you only need to estimate the sum or like the average of the variances so
Exactly.
far.
Exactly.
So, and that you have a chance of estimating more and more precisely as time goes by, as opposed to the individual quantities will never be.
Yeah, because this estimate only based on single single sum at this time. Yeah. Previously, we don't know how to do that.
Yeah.
But in MDP we can do that because it will repeatedly episode. But in Bandit it's a single
Single pool.
yeah. So we just do this one point estimation based on single. All right, then putting these two pieces of two key ideas together, right? Then we can show that the algorithm we propose, we call it the super lean ABE is adaptive first where exploration. The regret is upper bounded by this. And in the deterministic case, when the reward is deterministic, the regret will become O E. And it's computationally efficient. And also we don't need to know the variance of the loss at each row. All right. Then I think I may still have maybe 13 minutes, so I will briefly introduce the extension to linear trap DPs. So I think many of you are familiar with linear trap DPs because many of the authors of linear trap DP are also here. So it's very, I think it's a very nice model if you want to study reinforcement learning with linear function processing. The other one is linear MDP, which is also very interesting. But here I will focus on linear distribution. And we study homogeneous solid linear MDP, where the transition is called linear distribution, and there's this linear function, which is a feature mapping, and this feature mapping is known. The known feature mapping depends on SA, S prime is a triplet of state, action, and the next state. And the theta star is an unknown parameter with bounded as known. And the next thing about this linear MDP is you can show that for any function bounded by, for example, between 0 and 1, if you calculate this summation or integration, the resulting phi sub v will also be bounded by the same amount of the function itself. Okay? And based on this property, you can show that this operator is equal to phi sub v in the product with theta star. And the existing result for linear MDPs, I summarize them here. So the standard work on linear MDP is use the IO value targeted to the question by Yu and Jia and Kala and some other authors. And they proved that in the kind of homogeneous case, their required bound is B times swap H cubic times K. And the algorithm, as long as you assume this can be efficiently calculated, and the algorithm actually is efficient. And Matthew Dongwo and Kala and together we had a paper 2 years ago. We proposed an algorithm called UCRO with plus. So the idea is that instead of using the Hoffman type bonus, we are using the Bernstein type bonus to further improve the breadth of UCRO VTR. And the required bound can be is in this order, and it's a little bit messy, but as long as we assume E is greater than H, then actually it can be synthesized as E times swap of H cubic times 3. And this matches the lower bound in the time inhomogeneous setting. And in the first 2 papers, we assume the total sum, the total reward are bounded by H, which is the horizon rise.
If participation time is quality, why is velocity dependence on variance? Why is it not different?
Because in this MDP, at each time set, we assume the reward is bounded by 0 to 1. So the variance is also bounded by 0 to 1.
Sure, but why velocity dependence on like the empirical variance is much harder? No, Shabbos shaking his head, much harder. Okay.
Yeah.
That's what they do.
Yeah, and also the Bernstein inequality enable us to apply the total variance lemma, and that lemma can save us a factor of H. There's one thing I want to mention, because in the time homogeneous setting, this H cubic dependency is not optimal, because the first reality is not optimal, because they can also use Bernstein to further sharpen that requirement. And later, some paper by Zhang et al. And also King et al. They propose some computationally inefficient algorithm, because the algorithm involves some computation of a content set, which is which has actuarial dependence, and they consider the total reward is bounded by 1, and also homogeneous setting. The reason is they want to prove some horizon-free regret or horizon-free algorithm. And their regret bound is like some polynomial dependent on B times K plus some category. And last year, my student and I, we just follow the idea of how this work, but using a refined weight design. So we also come up with an algorithm, which in the worst case, it has a regret which is B times K plus D0. If you just ignore this D squared, this E times K, actually this is optimal because we can prove the lower. But this algorithm, for all these algorithms, they cannot give you the variance-dependent result. So a natural question is if we can derive variance-dependent algorithm or variance-dependent regret. And if we can do that, then the regret will also an instance-dependent algorithm or instance-dependent algorithm. Okay. And in particular, if the underlying MDP is deterministic, we hope the regret bound will not depend on number of episodes. Okay, and just using the idea I introduced for linear bandit, so we will apply similar idea to linear miniature MDP. And before that, I introduce a quantity which is called the stochasticity of MDPs. So if we define the variance of the function in that way, and then we just do summation, double summation. The inner summation is over sets, our summation is over episodes, and then we get this VER K-stop quantity. And this quantity actually measures how random or how stochastic the underlying MDP is with respect to the optimal value function. And for deterministic MDPs, this quantity will become 0. And we hope the regret bound we derive will depend on this quantity. Okay. And this is the algorithm, we call it
You probably lost connection to the internet.
oh.
Or I did, I'll check.
Oh, I think you did.
Oh,
I did.
Well, it's back.
it's back. Oh. Not back.
Oh, maybe it's now it's something happening.
Okay. Okay, so this algorithm is called using RAVE, adaptive variance aware exploration. So you can see that in this algorithm, we do not follow the security inclusivity kind of structure. We just use the bonus as the criteria, and then we assign the input feature mapping to the lowest layer, such that the bonus is without to max A. Okay, so it's very simple. So you can see that these two lines will just decide which layer you will assign the input context into.
So to clarify, you basically have a set of data sets sorted by the amount of variance at the time you observed it.
Yeah.
You filter it into one of these.
Yeah.
And then when you do the confidence interval, is it one per layer?
Yeah, one interval per layer.
And you pick the minimum of all the different layers. Or like how do you recombine?
Yes, yeah.
the
Well,
minimum?
you can see that when we calculate two bound layers,
Well, good to
across
know.
all the layers, because each layer can give you an
Yeah.
optimistic Q, and then you just go with the
What
smallest.
happens? So of course we will observe the next data point.
Uh-huh.
Your variances update.
Uh-huh.
What happens then? Like your confidence weights update, and do you have to throw all the data away and go again?
No. Because the update is incremental.
Update is incremental. Do you
Yeah.
then move the observations between the different layers?
No. Once the one is put into the layer, it will not be
upper
put out.
bound, it remains an upper bound.
Yeah,
So,
yeah.
Okay,
Yeah.
thank you.
Yeah, you cannot do that because actually we can only by doing this for example, add this contact vector into a layer, you just leave it there. And only under this condition you can prove that the number of contact vector in that layer is upper bound by 2 times L or times D, something like that.
Yeah.
Yeah, otherwise this property does not hold. And then with this algorithm design, okay, probably I would just
I see where these are. What Wi-Fi are you connected to?
一个叫 Albert Visit Wi-Fi.
Visit network. Could you?
Oh, okay. Then
You
now
only
I
have a
think
couple minutes.
Okay,
so
yeah.
Stick with it.
I will stick with it. Yeah, even maybe I just present it this way, like
Yes.
you see it. So okay, for that algorithm, I just introduce the regret bounded by D times square of this stochasticity quantity plus D square. And in the worst case, this can be bounded by D times K and plus D square. So this is the duet we obtained last year, but it's not the variance dependent. This is the new variance dependent duet we obtained.
Is it one of those variance dependent ones that sum with the horizon or not?
Some of the horizon.
Okay, so the variance is quite large and the horizon.
But the total reward is bounded by 1.
Okay.
So that's why it's bounded by.
I see, I see. Oh, okay.
Can you just show very quickly the definition of what star K?
Yeah.
Just, so the summation over the K is over what? So it's kind of what depends on K here? How does it like so what's the upper index SHK? What's the upper index K doing there? What is that? Is this dependent on the algorithm or?
Oh, it is dependent on the data.
Okay. But no matter what no matter what the algorithm does, if you are in a deterministic, you can limit this to T0.
Yeah.
But otherwise, it's an algorithm dependent quantity.
Yes.
Okay.
Yeah. That's correct.
Yeah. Okay.
All right. And okay, I think I already running out of time. So let me quickly wrap up this talk. So basically, I show you 2 sets of results. The first result is the first computationally efficient algorithm for stochastic linear bandit, which enjoys the variance-dependent duet. And the duet actually depends on the variance of the noise or variance of the reward. And when the reward becomes deterministic, the duet bound will also become nearly like a constant duet. And the second set of results is just extend this idea to linear mid-term DPs, and we get a variance-dependent duet, and like this one. It's a horizon-free algorithm, but it also matches the minimax lower bound universe. But we don't know that D square constant is optimal or not, because in the Bandit setting is D, but in linear mid-term DP is D square. We feel that D square is probably an artifact of our analysis. So that could be the remaining problem that we need further study. And in the future, we plan to generalize this idea to some nonlinear function class. And also, if we can derive a lower bound, variance-dependent lower bound, just like Andrew talked about that kind of lower bound, that would be even more interesting. That's all. Thank you.
So I guess. So I guess for your future work, for me, the most immediate future work would be, can you get rid of this data set slicing? Are you finally convinced that this is not true, or is it just kind of something that's for you a priority?
We don't know if this multi-layer data partition is essential. Because in one of my previous work, we have an algorithm, the correction class algorithm for linear bandit. And in the first version of the paper, I have actually mentioned there's multi-layer algorithm. But in the next version, we just change it to the healing technique improve instead of healing in algorithm.
Also, for many bandits you can do without any of the healing?
For correction, not for this, for a different type. So what I'm saying is, I cannot say that you for sure cannot get rid of the multi-layer structure, but at least I don't know how to get rid of that at the moment.
I sort of related to it a little bit. So I had this paper where we were looking at linear MVP, not the linear mixture MVPs. And we were trying to get some kind of like set of order kind of like variance dependent.
Yeah.
And what we ended up doing there was like we used like some Catoni estimators, which is like better. It's like Bernstein, but you don't have the lower.
I know that people.
I guess I'm just curious if you guys, because we didn't have to do any sort of like healing to get that position. Like we just like have an estimate. We just like basically use standard bonuses, but we just use a different estimator. I'm curious if you guys thought about sort of using some like different estimators at all. Like you could
I think the reason we need to do this multi-layer structure is because it's a new, we didn't have this problem. So and if you look at our proof is based on mathematical induction, following the idea of Bandits paper, Bandit and Wall paper, rather than using the moment method with the Abbas paper. And there's one step, which is a summation of the noise score times. And in my paper with Kala, we somehow use a universal upper bound for the variance, so that we can extract like sigma I square out of the summation and leave the summation of the bonus there. But in this beautiful for William inequality related reality, we extract the universal upper bound of the bonus out of the summation and leave the variance square inside the summation. So in that way, we can get this summation of the variance square, which is desirable in the Korean input. So that's the main difference in the two box computational problem. And in your paper, because you are still using the old computational problem, so that's why you don't need to worry about this bonus control, this fine grained bonus layer-wise control. But in our argument that we highly rely on that because we want to derive this variance-dependent derive. And also first order derive, I think is that only is still it's not variance. So,
Yeah, it's not very,
Yeah.
but yeah. Okay, I probably need to think more. I probably have to read your analysis part more carefully, but
Yeah.
yeah.
So any other question?
I'm just wondering, so there's another line of work about like first order or second order breakdowns
Yeah.
in adversarial independent.
Yeah.
And I'm wondering if your results is comparable to the results.
It's not directly comparable, but I think some of the technique here can be applied there because, for example, Andrew mentioned one of his work, the first order derive for linear MDP. I read that paper, very nice paper, and I also know some idea to do a different proof. But in the adversarial setting, I think that it's very tiny, depending on is a partial information feedback or full information. It's a full information feedback, I think it's easy. But if it is a partial information feedback, then the problem in the adversarial setting will become much more challenging. That's my current view. It may not be always the case, but because there's I always call optimistic policy optimization, and in their paper can only deal with linear track. But when they switch to linear MDP, actually, there are some proof that cannot go through.
I just wanted to re-ask Andrew's question about this Kaplan estimator and other robust estimators.
Yeah.
Because I think that really the question is whether you should change the estimator of the parameter and control things that I mean, like you're already changing it to take the various information into account. But I think maybe the hope there was that if you're changing the estimator to this robust estimator, that somehow magically you also win with the variance and like you cannot get that benefit without explicitly forcing the algorithm to estimate variances or do things like that. So have you thought about this?
Yeah. So I think that it's about just because when we go to the paper, and I think we also first try to
It's kind of a paid question.
yeah, like a media of meaning, something like that. But we didn't go through. When we first tried, then we tend to this weighted regression technique.
So I'm looking at the original paper you have to show right now. You do in the analysis, the final bound is like a sum of these like variance like terms.
Yeah.
The thing is, if you just like flipping at them because they could be like I think like You have to like, I believe you pay like an inverse variance.
Yeah.
In like a lower order term. And
Yeah.
You have to clip them to make that. Small.
Yeah, yeah.
And so when you get to some of the variances here, it's not the true variances, they're like clip variances, and that's like,
Yeah.
screws it up to very kind of bound.
Yeah.
The thing is with Pitoni, you don't have to clip the variances
Mhm.
because you can sort of get rid of that lower order term. So I guess the hope might be like this analysis that you have in your original paper.
Uh-huh.
You could do something like this with Pitoni. You
Yeah.
don't have to clip the variances.
For
And then-
MPP, I agree, but for the, I think the
For Bandits, yeah, I don't think so.
yeah, for Bandits, you
Yeah,
only
yeah.
observe each reward once.
Yeah.
So that's
Yeah, for sure.
right.
You're right.
Right. But for MPP, I think there might be other alternative ways and make the form cleaner.
Okay.
Yeah.